Like and subscribe. 1. Introduction. Switching operations are a major source of power system transients. For instance, capacitor bank switching can create current surges and overvoltage. Energization operation can create a significant DC offset that can, in turn, saturate power transformers. Shunt reactor de-energization can cause CB reignitions that can result in equipment failure. Transformer energization typically creates significant inrush currents that create harmonics in the voltage and current signals. In addition, the protection schemes need to account for situations such as the failure of the pre- and post-insertion resistors and be able to bypass such failures in a timely manner. The aim of power apparatus controlled switching is to reduce and possibly eliminate these transients and, therefore, contribute to protecting the power equipment, improving the power quality and reliability. The combination of CBs with stable closing and opening characteristics and present-day digital technology has allowed intelligent controlled switching devices to be devised that can be applied to any equipment type. Controlled switching is best implemented with breakers with independent pole operation. 2. Controlled switching basic principles. The controlled closing of a power apparatus consists of triggering the electrical make of a CB pole contact at a desired voltage point on wave angle. This operation reduces or eliminates voltage or current transients that can result from closing in a random fashion. The nature of the voltage or current transients depends on the equipment type being energized. Desirable characteristics of a CB for use in controlled switching applications are: circuit breaker operating time. The operating time in a CB is the average time interval between the instant when the voltage step is applied on the CB pole closing coil and the instant when the two sides of the pole contacts touch. The following are the main influencing factors which can be compensated. Typical parameters such as control voltage, stored energy of the drive, and ambient temperature are often compensated for by the controller. Increment comp equals F. The idle time dependence of the drive is another factor that can influence the mechanical switching time of each CB operation. Electrical characteristics of circuit breakers operation. There is a certain voltage level at which the contact gap will break down and current will be initiated for a given contact gap. When interrupting small capacitive currents, there is a certain probability of reignition for particular CBs, depending upon the contact gap at current zero and the RRDS. The application of controlled capacitor de-energization facilitates current interruption with a relatively large contact gap, as dielectric strength can be increased with a contact gap. The application of CSS for small capacitive current interruption can avoid small arcing times and, therefore, the dielectric stresses and reignition probabilities can be markedly reduced. When interrupting small inductive currents, there is again a certain probability of reignition, as the contact gap at current zero may not be sufficient to withstand the recovery voltages, which is determined by the chopping current levels and load characteristics. The arcing time, and therefore the contact gap at current zero, should be sufficiently large to ensure interruption without reignitions. The making instant is when the voltage across the CB exceeds the dielectric withstand strength of the contact gap. As the CB contacts approach each other, the voltage across them may exceed the dielectric strength of the insulating medium, resulting in dielectric breakdown. Prestrike characteristic at a voltage peak coincides with the voltage sine wave slope at a zero crossing. The statistical nature of dielectric breakdown has a significant influence on the RDDS. The actual withstand of the contact gap is a statistical property and exhibits some scatter, which may be given by the standard deviation of the withstand voltage distributions. When selecting a CB for a controlled switching application, the CB scatter should be lower than a specified value of 3 where the majority of operating times will fit. During load interruption, the rate at which the withstand voltage between the CB contacts rises as the contact gap is increased is known as the RRDS. CBs with high RRDS values can interrupt inductive loads without reignition, as the CB dielectric withstand exceeds the transient recovery voltage across the CB terminals. TRV is the voltage that appears across the CB contacts immediately after current interruption. A TRV with a steep rate of rise or high amplitude can lead to reignition or restrike following current interruption. Normally, during CB opening, the CB main contacts are moving more rapidly than for the closing operation. Otherwise, the opening operation will not be successful and a reignition or, worse, a restrike could occur. Controlled de-energization. In this example, the controller detects periodical current zero crossing as the reference synchronization signal. The arcing time of each pole is controlled by setting the instant of contact separation with respect to the current waveform. It can substantially reduce the probability of restrike during consecutive capacitor de-energization or avoid reignition in the event of reactor de-energization. Controlled energization at voltage 0. The example relates to a discharged capacitive load, where the optimum making instant is the voltage 0, which can be attained with an ideal CB with infinite RDDS with no mechanical scatter. A pre-arcing before contact touch is not considered. In the event of an inductive load, the optimum making instant to reduce the inrush current is the voltage peak as shown in Figure 4, where the pre-arcing time between the instant of pre-strike and contact touch is assumed to be an eighth of a cycle. Controlled switching of transmission line. The physical phenomenon governing line switching over voltage is the propagation of electromagnetic waves along the line, generally called traveling wave phenomena. The wave propagation is initiated by the CB making operation, and the initial voltage amplitude is the CB pre-arc voltage, i.e., the instantaneous value of the voltage across the CB pole at the line charging current making instant. As shown in Figure 5, energizing occurs at an instant with a large difference between supply voltage and line voltage, when a large traveling wave will be injected onto the line. When this wave reaches the open, far end of the line, it will be reflected and a high overvoltage will be initiated. Controlled reclosing of the CB aims to minimize the initial voltage difference between the supply and the line, and thereby the switching transient. Control of closing and reclosing operations, uncompensated lines. The delayed targeting is determined by the CB RDDS with respect to the amplitude of the system voltage and its frequency. This will be the case when sufficient time has elapsed from the opening operation, or even at reclosing operations, if the line is equipped with magnetic voltage transformers. The method gives best results with CBS with high RDDS. As shown in Figure 7, the CVTs will show the DC voltage level related to the trapped charge for a certain time interval after interruption, and this value will be used by the controller. Should the time interval before reclosing exceed 20s, the controller will automatically change to the assumption that the line is uncharged. Control of closing and reclosing operations, shunt compensated lines. In this case, due to the oscillating voltage shape on the line, the voltage transformers connected to the line will provide correct voltage signals. Reclosing may be set to occur slightly after phase to ground supply side voltage 0. Controlled switching of shunt reactors. Their function is to consume the excess reactive power generated by overhead lines under low load conditions and thereby stabilize the system voltage. They make the three phases magnetically independent, while three-leg cores leading to magnetic coupling between the phases. De-energization operations for shunt reactors. Due to chopping of the current slightly before the natural current 0, the oscillating reactor voltage will have a higher amplitude than the supply voltage. Due to the oscillating reactor voltage, there will be a high voltage stress across the CB. A reignition will generate high-frequency transients in both reactor voltage and current. Following a reignition, the reactor current will be interrupted again either at a high-frequency 0 of the current, or most probably at the subsequent power frequency 0. Controlled opening by optimizing arcing times and separating arcing contacts within the free reignition window allows the reduction of current reignition probability and increase of equipment lifetime. Controlled switching of power unloaded transformer. In steady-state unloaded conditions, all the magnetic flux is well contained inside the transformer iron core, so only a small magnetizing current is needed, as shown in Figure 10. Figure 10, electrical and magnetic signals in steady-state condition. As is well known, when a high-voltage power transformer is de-energized, it keeps some residual flux in their iron cores, which may affect the inrush current magnitude at the next energization, depending on the energization instance. As transformers are normally energized by arbitrarily closing the CB contacts, with the system voltage being applied on the transformer windings at random instants, this switching operation may introduce an asymmetrical magnetic flux in the windings, driving the transformer core into saturation. This will produce an inrush current whose